The proof of law of cosines is actually a fairly straightforward thing, but it takes a little bit of thinking outside of the box. The idea behind it is we want to verify something, so we're going to verify, in this case, we're going to verify that a squared equals b squared plus c squared minus 2bc cosine of a. And if we prove this version, we'll really essentially have proven all three, because I could go and relabel this triangle as CAB, and then I could do the same sort of thing that I'm going to do in this proof, and instead of the little a being here, this would be little c, and so it'll just change the form. So that's easy enough to do. What we're going to do, first of all, is acknowledge that right triangles are a lot easier to work with in this world. You study Pythagorean Theorem a lot, you study basic SOHCAHTOA trigonometry, so we're going to drop in an altitude for this triangle. That's going to provide us with a height. We'll just call that h. That's pretty standard for height. And what we're going to do is use our knowledge of a right triangle situation to put together a few true statements. In order to do that, though, I need to talk about the lengths of these smaller sides that I just created. I don't really want to talk about little c as much. So what I'm going to do is I'm going to label the length from here to here as the length x. And if this little piece here is x, the remainder of this whole side that I've chopped off would be this whole side c minus this part x. So here, this is c minus the length x. So that's a little bit squeezed in there, but that's okay. So we have x plus c minus x. If you wanted to verify that, you could see that if I added the side length of x plus the length of c minus x, this x and this negative x would knock each other out, and we would get the whole length of c. So that feels appropriate. Now I'm going to make two statements that are technically true, and hopefully this is okay. If I wanted to know cosine of big A, keep in mind that we need to work with cosine of A here, right? That's in our formula. We need to know that that's there. If I go up here, noticing that, of course, this is also a right triangle on this side, cosine is always going to deal with the adjacent side of your right triangle over the hypotenuse of that same right triangle. Cosine of big A in this problem would have to equal x over b. Now, we also know that we can set up, right triangles always use the Pythagorean Theorem, so we can set up a couple things there. What about b squared? B squared is up here, well, rather b is, but if I wanted this to be b squared, we'll just say and, we know that b squared, if I wanted that in my problem, is going to equal x squared plus h squared. Pythagorean theorem says the side length squared plus the side length squared equals the hypotenuse. So this is x squared plus h squared. Now I could go on all day and come up with a bunch of different other things here, but what I'm going to do is go ahead and make one last statement using the other right triangle. I'm going to do the same thing I did here, except it'll look a little messier. I want to deal with a squared, so let's go ahead and do that. A squared, because it's the hypotenuse, would equal this leg squared, and it would equal this height squared. So h squared plus c minus x squared. So take a moment, make sure you're up to speed with me on this. Cosine is adjacent over hypotenuse. Pythagorean theorem says that the legs squared and added together give me the hypotenuse squared. Same thing here, leg squared plus leg squared equals hypotenuse squared. And I go, well look, I cannot really do much with c squared because it's not part of a right triangle. It's part of this bigger obtuse triangle, so really I'm pretty much done with what I can find out of here. I've already got b, I've already got a, I've already got big A, and that's about as much as I can pull out of this. And in fact, if I look down here, technically speaking, c squared's hiding inside of this. So I feel like all my pieces are in place. I think these three statements are enough to work with. And so what I'm going to do is go, well look, in this formula here, there's no x and there's no h. So I need a squared to equal stuff with just b, c, and big A. I need this h, and this x out of the problem. Let's first of all go ahead and simplify this part here as much as we can. Let's go ahead and multiply that out. When you multiply a binomial, you square the first term, you double the product of these two guys, so we get minus 2cx, and then you square the last term. Now that looks like I've made it more complicated, but I can assure you this will be okay. Let's go ahead and replace the easiest pieces first. If I look over here, I see h squared already. I can easily get that by itself by subtracting x squared from both sides. And what I mean by that is that h squared is going to equal b squared minus x squared. So I subtracted x squared from both sides. So I can replace this h squared down here. This is good news for me. If I've got a keen eye, I can tell that this is going to actually help me a lot. This minus x squared and this plus x squared now, when we combine like terms, are just going to cancel each other out of the problem. If I give you something and then I take it away, it's just gone. And this form is starting to look very familiar now, actually. I feel pretty good about this. I see b squared plus c squared. That's already a great start for me. And I see minus 2c times x. So the last thing I need to deal with is our little x. And I go, well, look, there's one formula I haven't worked with yet that has x in it. And it also has the cosine of big A, which I'm still missing. It also has the little b, which is supposed to be paired up with this c. Let's go ahead and solve this for x. It looks like x would equal b cosine of A. Notice that all I've done is multiplied both sides of this equation by b. I've brought it up to the numerator of this side. And that's great news there. If I replace this x with b cosine of A, and then I just do a little bit of rearranging real fast, we're going to see, in fact, that it is true that a squared does equal b squared plus c squared minus 2bc cosine of A. And there we go. We've proven that theorem.